Hi, hello, I'm Kiran Kumar from Nature of Physics and Art. Welcome to my channel. Today's topic is electric field intensity and electric potential of a non-conducting solid sphere. First, I will explain the electric field intensity based on the Gauss law and electric potential based on the EVD relation. From last 5 videos I am doing first electric field intensity and electric potential in one video. Please watch that videos also. Please do subscribe my channel and share these videos to your friends also. So first, considering this is the solid sphere that is non-conducting, that is uniformly positive charged. Capital R is the radius of the solid sphere and small r is the radius of the Gaussian sphere. Okay, so here electric field intensity we wanted to find. S is the surface area of the Gaussian sphere and ds is the small element area and ds bar is the area of vector. Electric field is radially outward direction and theta is equal 0 because of E bar and ds bar along the same direction. Okay, so here we can find the electric field intensity outside the outside the solid sphere and on the solid sphere and inside the non-conducting solid sphere also, step by step. So first one is, that is volume charge density. Volume charge density, that is rho, which is equal to Q divided by volume. Volume is equal to here 4 by 3 pi r cube. Okay, so first condition here, small r is greater than to capital R. So small r is the radius of the Gaussian sphere, that is outside the non-conducting solid sphere. So then small r is greater than to capital R, that is E outside the electric field intensity of the solid sphere. Okay, for this I am considering Gauss law. So Gauss law is closed integral E bar dot ds bar, which is equal to Q divided by epsilon naught. Okay, so for this theta is equal 0 and cos 0 is equal to 1. So we can write closed integral E ds cos 0, which is equal to Q divided by epsilon naught. Here cos 0 is equal to 1. So here the value is, okay, that is E into closed integral ds, which is equal to Q divided by epsilon naught, and E into integral ds value is 4 pi r square, okay, which is equal to Q divided by epsilon naught. So electric field intensity outside the non-conducting solid sphere, which is equal to 1 by 4 pi epsilon naught Q divided by epsilon naught. Okay, or we can write E out, which is equal to KQ divided by, here r square. Okay, KQ divided by r square. Okay, so this is the equation for electric field intensity outside the non-conducting solid sphere. Okay, so one thing try to understand here, we can replace the Q value. So Q is equal to rho into 4 by 3 pi r cube based on the applications only. So here I am not replacing, but try to remember that value. Q is equal to rho into 4 by 3 pi r cube. Okay, and next one, second. For second, electric field intensity on the surface. So on the surface, just I am replacing small r is equal to capital R in the above equation, that is E on, which is equal to 1 by 4 pi epsilon naught Q divided by capital R square. Okay, R we can write E on, which is equal to KQ divided by capital R square. So here small r is equal to I wrote capital R, here also small r is equal to I wrote capital R. So this is electric field intensity on the surface of non-conducting solid sphere. Then inside we will discuss. Just 1 minute. Now, third one is electric field intensity inside the non-conducting solid sphere. For this, I'm using same formula already. We did applying the Gauss law and we got the equation E outside is equal KQ by R square. Even inside also we will get same only, but inside there is a charge. But hollow sphere, that is metal sphere, there is no charge, that's why electric field intensity is 0 inside. But here electric field intensity present because of inside is charge available. Okay, for that I'm using the same formula, that is E in, which is equal to K Q in divided by R square. See, small r is the radius of the Gaussian sphere and capital R is the radius of the non-conducting solid sphere. That's why here the charge available in the Gaussian sphere is Q in I am considering. Already we know one formula, rho is equal Q divided by 4 divided by 3 pi r cube. I'm using that formula. So rho, which is equal to Q divided by 4 pi 3 pi r cube, which is equal to Q in divided by 4 pi 3 pi small r cube. For capital R, charge is equal to total charge Q. For small r, the total charge is Q in. So from these two equations, 4 by 3 pi is get cancelled. From this equation, Q in, which is equal to that is, the value is Q into small r cube divided by capital R cube. See, Q in, which is equal to Q into small r cube divided by capital R cube. This value is replacing in the above equation. So the resultant equation E in, which is equal to Q in value I will replace K divided by R square, and Q in value is Q into R cube divided by capital R cube. Okay, R square R cube is get cancelled. So we got here E in, which is equal to K Q R divided by capital R cube. Or another equation is E in, the K value is writing 1 by 4 pi epsilon naught Q into R divided by capital R cube. So this is the electric field intensity inside the non-conducting solid sphere. But electric field intensity in a metal sphere, okay, their electric field intensity is 0 because of inside there is no charge. That's why electric field is 0. But here electric field is available because of inside charge is available. Okay, just a second, I will clean the board and draw the graph, that is electric field intensity outside on the surface and inside the non-conducting solid sphere. Now graph, that is electric field intensity and radius of the Gaussian sphere. First condition is R is greater than to capital R. In this, E out, which is inversely proportional to the R square, and E on the surface, small r is equal to capital R. Capital R is the radius of the solid sphere, small r is the radius of the Gaussian sphere. So E on, which is equal to, that is also inversely proportional to the R square, and next E in, so that E in, that is E is directly proportional to the small r, that is E on, which is equal to KQ divided by R square. Because of here we have on the x-axis is small r, that's why here small r is equal to capital R. That's why this is on the surface, E on the surface, which is equal to KQ divided by R square, and this is E outside, which is inversely proportional to the R square. And here E in is like this, E in is directly proportional to R. Electric field intensity increases inside and radius also increases. That's why E in is directly proportional to R, that is straight line passing through the origin. On the surface is KQ by R square, and outside the surface is E outside is inversely proportional to R. That's why this is hyperbola. So this is the graph for the electric field intensity of non-conducting solid sphere. On the x-axis is R is the radius of the Gaussian sphere, and E is the electric field intensity. Okay, just a second, I will explain the electric potential based on the again three equations from the EVD relation. Okay. Now continuation, electric potential of a non-conducting sphere. See, electric potential I am doing with the help of EVD relation. So for first one is small r greater than 2 capital R, electric potential outside the solid sphere. Outside the solid sphere. So capital R is the radius of the solid sphere and small r is the radius of the Gaussian sphere. So here the formula V, which is equal to or dV, which is equal to minus E into dr, and integration on both sides. See here, integral dV is equal V, that is V out, which is equal to minus of integral E in value is E outside value is KQ divided by R square into dr. Okay, so V out, which is equal to minus KQ divided by R square, okay, and R to the power of minus 2 plus 1 by minus 2 plus 1. Okay, so this minus value is get cancelled, so we will get V out, which is equal to KQ divided by, okay, this is R square is get cancelled, KQ by R. So V out, which is equal to 1 by 4 pi epsilon naught Q divided by R. Okay, so this is from EVD relation. We are finding the electric potential outside from the electric field intensity outside. Now V on the surface, second one. So small r is equal to capital R. Okay, here just I am replacing the values. Here small r is equal to capital R, here small r is equal to capital R. Again I don't want to do the derivation. So that here V on the surface, which is equal to KQ divided by capital R. Here V on the surface, which is equal to K value rating 1 by 4 pi epsilon naught Q divided by capital R. Just a second, I will continue with electric potential inside the non-conducting sphere. See now, continuation here, V in, which is equal to here KQ divided by R is common. So then 3 divided by 2 minus R square divided by 2R square. See, 1R is common, R square is remaining same, only small r square. Okay, so here we can replace the equation K value 1 by 4 pi epsilon naught. So V in, which is equal to 1 by 4 pi epsilon naught Q by R into 3 by 2 minus small r square by 2R square. This is the first equation. This is the second equation. Here we can write in the second equation small r is equal 0 at the center of the non-conducting solid sphere. For that small r is equal to 0. Okay, so that is VC at the center, that is KQ divided by R. Okay, here 3 divided by 2. This value is 0, 0 by anything is 0. So we can write here 2 ones, then 1.5. So VC, which is equal to 1.5 times the V on. Vc is equal how much? 1.5 times the V on. Okay, just a second, I will continue with graph. Now, electric potential graph with radius of the Gaussian sphere. See, first this is on the surface, so that on the surface V on, which is equal to KQ divided by R. This is small r is equal to capital R V on. Okay, and continuation, first outside. So outside is here potential now. V outside is inversely proportional to the small r, that is hyperbola. V out inversely proportional to r. Okay, and then continuation here, next V inside. So the graph is like this. Okay, so V in value is, we got KQ by R 3 by 2 R square divided by 2R cube. Here this is VC value. So here VC value already I gave you. Okay, 1.5 KQ. Thank you, and please watch my videos and do like and subscribe my channel Nature of Physics and Art. Thank you.